Jai Hind students, welcome to my physics classes. Students, life is some days a bed of thorns, a puddle of mud, a pothole on a highway, and it might deny you happiness. But always remember, students, life is going to respond to your attitude, and happiness is always a choice. So develop that attitude to be always positive and to remain always happy. So students, keep smiling.
With that positive note, students, let's begin this particular session. Here in this lecture, we'll be discussing the topic of interference of light. Now, students, we all are aware of the wave theory of light. As per the wave theory of light, the light emitted from a source travels in a medium in the form of waves. Now, when there is a single source of light, then the distribution of light energy in the surrounding medium is uniform in all the directions. But when we have two sources of light emitting continuous waves of same wavelength and preferably of same amplitude, then due to the superposition of the waves from these two sources, the distribution of light energy no longer remains uniform in all the directions. And students, this phenomena of non-uniform distribution of energy in the medium due to the superposition of the two light waves is known as interference of light. And we will discuss that there are certain regions where the intensity of light is found to be maximum, and there are also certain other regions where the intensity of light is found to be minimum. So actually what happens is that the energy due to these two sources due to superposition is redistributed. And as I've told you, this redistribution of light energy obtained as a result of the superposition of the light waves from the two sources of light is what we call as the interference of light. So basically, the phenomena of non-uniform distribution of energy. The phenomena of non-uniform distribution of energy in the medium, right? In the medium due to the superposition of the waves, due to the superposition of light waves. It is known as the interference of light. Now, before we discuss interference of light in detail, we must understand the concept of superposition of waves and the principle of superposition of waves, right? So students, in order to understand this concept, let us watch this animation.
When two or more waves superimpose upon one another, then it results into a new wave. In order to understand this, let us consider a simple analogy. When a body like a nail is dropped in a pool of water, then waves are produced. These are known as water ripples. Now when these two waves interfere, then as per the principle of superposition, the resultant displacement of a particle at any instant is given by the vector sum of the individual displacements caused to the particle by the two or more waves. This principle can also be stated for two or more waves superimposing upon one another. Thus, the new wave has resultant displacement at any instant which is equal to the vector sum of the displacements due to the individual waves at that instant. So, if we consider y1 and y2 be the displacements of the particle respectively at any instant caused by the two waves, suppose y1 is the displacement due to the first wave, and consider y2 to be the displacement caused at the same instant due to the second wave, then when they superimpose, then the resultant displacement is y1 vector plus y2 vector. And in case they are in the same phase, then it get added up. So therefore, in constructive superposition, the amplitude and hence the intensity of the resultant wave after superposition of the two waves increases. So crest of one wave falling on the crest of other, or the trough of one wave falling on the trough of other, results into maximum displacement. While on the other hand, when crest of one wave falls on the trough of other, then it results into destructive superposition where the amplitude and intensity is minimum.
Friends, what we have discussed is principle of superposition of waves states that when two or more waves travel in a medium in such a way that each wave represents its separate motion individually, then the resultant displacement of the particle of the medium at a given time is equal to the vector sum of the individual displacements, right? Let me elaborate it again. Suppose this is wave 1. Let me draw this wave 1, this crest and this is trough. This is crest and then this is trough. This is wave 1, suppose. And let us consider this to be other wave, wave number 2. And both are in the same phase, that is, they are in the same state of vibration. Let us consider both the waves are in the same state of vibration, right? So what happens is, suppose its displacement is A. Its displacement is also A. Maximum displacement, that is amplitude. So it is Y1 and suppose it is Y2. Now when these two waves superpose with each other, then what happens is the crest of one wave falls on the crest of the other, or the trough of one wave falls on the trough of the other. So at the points where the crest of one wave falls on the crest of the other, or the trough of one wave falls on the or over the trough of the other wave, then what happens is the resultant amplitude of the resulting wave is maximum, because as per principle of superposition, the resultant displacement is given by y1 vector plus y2 vector. Here, since both the waves are in the same state of vibration, that is, they are in the same phase, therefore y1 is equal to plus a, y2 would be also equal to plus a. So net displacement at a point would be equal to twice a, isn't it? Because they are superimposing in the same phase. So the resultant wave would be somewhat like this. Here the amplitude is maximum and hence the intensity is maximum. This corresponds to the constructive superposition and results into constructive interference, right? So basically what happens is, at these points where crest of one wave falls on the crest of other, or the trough of one wave falls over the trough of the other. So at these points what happens is the intensity of the wave is maximum, and this is known as constructive interference, right? So here the amplitude, it will be twice A. So this is the reference line. So these are the two waves which are superimposing in the same phase, and it results into constructive interference. So at the points where crest of one wave falls over the crest of the other wave, then the resultant amplitude of the wave would be minimum. That we'll discuss in the second part, right? So this was regarding constructive interference, where the amplitude, displacement and hence the intensity of the resulting wave is maximum. Let us draw the diagram in the case where the two waves under consideration superimpose out of phase. Suppose this is wave 1. This is the crest, this is the trough. This is the crest and this is the trough, right? This is wave 1. And suppose this is wave 2. Wave 2 is out of phase. These are the two waves which are oscillating out of phase. Out of phase means having opposite phase angle of 180 degree, or they are vibrating out of phase, isn't it? So here what happens is the crest of one wave falls over the trough of the other wave, or the trough of the first wave falls over the crest of the second wave. In such a case, what happens is the resultant amplitude or the intensity of the resultant wave is minimum. And students, if it happens that these two waves are of the same amplitude, in such a case, y1 it would be equal to plus a and y2 it would be equal to minus a, because they are out of phase. They are in the opposite phase of vibration, isn't it? So here resultant displacement, it would be given by plus a plus minus a. That will be equal to 0. So students, in case the two waves are of the same amplitude, then at the points of destructive interference, in case of light, then the intensity of light is 0. That is, complete darkness will result. Complete darkness will result. So this corresponds to the case of destructive interference. Students, in the case of constructive interference, the amplitude is maximum and hence the intensity of the resultant wave is also maximum. While on the other hand, in the case of destructive interference, that is when the two waves superimpose out of phase, that is two waves superimpose with crest of one wave falling over the trough of the other or vice versa, then it results into destructive interference. Here, as from the diagram it's pretty clear, the amplitude is minimum and hence the intensity of the resultant wave is minimum. Right? Now students, on the interference of light waves, we will obtain alternate bright and dark bands of light. These are known as interference fringes. We'll be discussing it in detail. And it should also be understood that in interference of light, energy is neither created nor it is destroyed. The energy that disappears at the point of destructive interference appears at the points of constructive interference and vice versa. Thus, in the interference of light, simply redistribution of light energy takes place and the energy gets redistributed. And this phenomenon of non-uniform distribution of energy in the medium due to the superposition of waves, it is known as interference of light. In 1801, Thomas Young demonstrated the interference of light experimentally. Actually, his experiment gave a deadly blow to the corpuscular theory of light, as the experiment led to the conclusion that light has wave nature. So students, let's try to understand Young's double slit experiment, which is YDSE, Young's double slit experiment, with the help of this animation, and then we will recap the entire thing.
When the waves are made to pass through two slits, then due to the superposition of the waves, the energy distribution no longer remains uniform. At certain points, the intensity of the wave is maximum, while at certain other points, the intensity of the wave is minimum due to the superposition of these waves. Thus, the energy is redistributed due to the phenomenon which is known as interference. Now, as the waves superimpose, then if a crest of one wave falls on the crest of the other, then it results into constructive interference. While on the other hand, when the crest of one wave falls on the trough of the other, then it results into destructive interference where the intensity is minimum. The phenomena of interference in light was demonstrated by Thomas Young in 1801. He allowed sunlight to fall on a fine narrow slit S. The light waves from S spreads out in all the directions. These waves were made to fall on two very fine slits A and B, which were parallel and very close to each other. A and B were equidistant from S. These slits A and B give waves of same wavelengths and nearly same amplitudes. These waves were superimposed on each other and gave rise to interference. Alternate dark and bright bands were obtained on a screen placed at a certain distance from the plane of the slits A and B. As per Huygen's principle, slit S sends wavefronts in all the directions, and the slits A and B become the source of the secondary wavelets, which are in phase and of same frequency when they reach point O on the screen, and hence the center of the screen, the intensity of the light is maximum. So therefore, the alternate bright and dark bands called fringes appear at equal spacing on the screen. And this redistribution of intensity of light on account of the superposition of the two waves is called interference.
Students, let us recap the entire thing. Here, S is a source of monochromatic light and it is used for illuminating these two narrow slits S1 and S2. These two slits lie very close to each other and at equal distances from the source. That is, SS1 is equal to SS2. Now the wavefronts from the slits S1 and S2 will spread out in all the directions and in the region they superimpose on the screen, right? And then alternate bright and dark fringes will be observed. This we will discuss again with the help of this diagram. So basically here the disturbance will travel in this form. Suppose this is the crest and this is the trough. So the disturbance will travel in this form, in the form of crest and trough, right? I am drawing with the help of these concentric circles. So what happens is, since S1 S2 both are equidistant from S, therefore these two, the waves emitted from these two sources S1 and S2 will be initially in the same phase. That is, if it is represented by this dark line, then it will be also initially represented by this dark line. So let us continue drawing these waves in the form of crest and trough. Now this is how the wave fronts from the slits S1 and S2 will spread out in all the directions, and in the region they superpose on the screen alternate bright and dark fringes will be observed. Now students, here suppose the dark line, suppose this dark line, this represents crest, and let us consider this dotted line, this represent trough. Now students, we have already discussed when the crest of one wave falls on the crest of other, that is like this, when the crest of one wave falls on the crest of other, or the trough of one wave falls over the trough of the other, then it results into constructive interference. It results into constructive interference where the intensity of light would be maximum. While on the other hand, and this constructive interference are represented by this, at this point it will result into maximum intensity. I'll represent it by this dark dot, right? While on the other hand, if the crest of one wave falls over the trough of the other, like this, dark line and dot line, the intersection of one dark line and the other dot line, it will result into destructive interference. It will result into destructive interference where the intensity of the light would be minimum. And in case the waves comes from the two sources which are derived from the same original source, then these two waves emitted from S1 and S2 will have the same amplitude, and thus at the points of destructive interference, complete darkness will be observed, right? Amplitude and hence the intensity would be zero at points of destructive interference. So for destructive interference, I will denote it by square like this, and I will darken it. So circle, that will represent constructive interference, square it will represent destructive interference, right? Now students, coming to the diagram. Now look, over here crest of one wave meeting the crest of the other wave. So it will be the case of constructive interference. I'll show it with the help of circle, right? Filled dark circle. Here again, the trough of one wave falling on the trough of the other. It will result into constructive interference. Crest of one wave falling on the crest of other, constructive interference. Again here constructive interference. Again here constructive interference. So if you join this line, then at this point on the screen, students, the intensity of the light would be maximum, isn't it? So this is known as the central maximum, right? This is point 2, which is the center of the screen. Here the intensity of the light would be maximum because this will be the point of constructive interference. Again students, let's check it out. Here students, see, this is the intersection of dark line and dotted line. Dark line and dotted line will result into destructive interference, just now we have discussed. So it can be represented by square like this. Here again, crest of one wave falling on the trough of the other. So it will be the case of destructive interference. Here it is the case of destructive interference. So here it is the case of destructive interference. So if you join these points over here, in such a case, you will get this point. This will be the point of the first dark band. Similarly, on the other side of the center of the screen over here, this is the point of destructive interference. Here again, crest of one wave falling over the trough of the other. So these all are the points of destructive interference. So if you connect these points, students, if you connect these points on the other side of the screen also, this will be the position of the first dark band where the intensity of the light would be minimum. Similarly again students, here look, trough of one wave falling on the trough of other. So it is the point of constructive interference. This is also the point of constructive interference. So these are the points of constructive interference where either the crest of one wave falls over the crest of other or the trough of one wave falls over the trough of the other. So if you connect these points, we'll get the position of the first bright band where the intensity of light is again maximum. So this is the position of first bright band. Clear? Similarly on the other side of the screen over here, look, trough of one wave falling on the trough of the other. So this must be the position of constructive interference. Here crest of one wave falling on the crest of other. Again constructive interference. So these dots represents the positions of constructive interference. So if you connect these points, we will obtain the location or the position of a point on the screen where the intensity of light would be maximum. And this will be the position of the first bright band like this. Students, in the interference pattern, we obtain a central maxima which is surrounded on both the sides by alternate dark and bright bands. It is known as interference fringes. This is the center of the screen where the intensity of light is maximum, which is followed by a dark band. This is the first dark band, this is D1. While here again the intensity of light is maximum, so this is the first bright band. We will mathematically justify that the width of the central maximum, the width of the dark band and the width of the bright band all are equal. That is, in the subsequent lectures we are going to prove that beta naught is equal to beta D is equal to beta B is equal to beta C. That is, in the interference pattern where we obtain a central maxima which is flanked on both the sides by alternate dark and bright bands, the width of the central maxima, all the bright bands, all the dark bands, all are equal. Now students, it should be noted that the interference pattern over here which we have obtained will completely disappear if one of these two slits S1 and S2 is closed. So basically this happens, or rather this confirms that interference pattern is entirely due to the superposition of the waves from the two slits, right? And one more important point is, if instead of two slits illuminated with a source, two independent sources are used, then the interference pattern obtained on the screen is not permanent one, or the positions of these bright and dark bands, it keeps on fluctuating. It is not permanent one, and the positions of maxima and minima do not remain fixed. This observation confirms that for producing a sustained interference pattern, two sources must be produced from a single source, and such a source are known as coherent sources. One more important point to be noted is that here we have made use of a monochromatic source of light, that is, which emits single wavelength, single color. So there the interference pattern consists of a central maxima which is surrounded both the sides by alternate dark and bright bands. But if instead of using a monochromatic source of light, if a source of white light is used, then the interference pattern obtained on the screen are colored and their widths are also different, because the widths depend upon the wavelength, and wavelength of different colors is different. Now students, sustained interference, we have discussed that it is the interference pattern in which the positions of maxima and minimum of intensity of light remain fixed all along the screen. So such an interference is known as sustained interference. For producing sustained interference, there are certain conditions which need to be satisfied. Let's discuss those conditions. The two sources must emit waves continuously. This is the first condition. The two sources should emit the light waves continuously. Here I must like to mention that in practice a sustained interference pattern cannot be obtained by using two independent sources of light, howsoever alike they may be, but independent sources of light cannot be used to produce sustained interference pattern, because by using independent sources of light, this first condition cannot be obtained. That is, two independent sources of light cannot emit the light waves continuously. So sustained interference pattern can be obtained only when coherent sources are used. Now students, coherent sources are those sources which are derived from the same parent source, right? I mean, the two sources are derived from a single source, and such sources are called coherent sources, right? So let's discuss the second condition for obtaining sustained interference. The light waves emitted by the sources must be of same wavelength. So the light waves emitted should be of same wavelength. Third is, students, they should preferably of the same amplitude. They should be of preferably be of same amplitude. And as I've stated, students, in case the two waves of same amplitude interfere or superpose out of phase, so at that point obviously the intensity would be zero, that is, complete darkness will be observed, right? So if the amplitudes of the waves are equal, then the dark fringes are completely dark, that is, the intensity of light is zero. Fourth point is, the waves emitted by the two sources of light, it should either be in phase or should have a constant phase difference, right? This is a very, very important point. So, the waves emitted by the two sources of light should either be in phase. That is, they should either be in the same state of vibration or should have a constant phase difference. Should have a constant phase difference. So this is the condition which needs to be satisfied so as to obtain sustained interference pattern. Clear, students? Now, as I've told you, by using independent sources of light, one is it cannot emit the light waves continuously, and also by using two independent sources of light, the waves emitted by the two independent sources of light do not have a constant phase or constant phase difference. Because, students, you are aware, the light emitted by each excited atom of the source, which are maybe millions, billions in number. So an excited atom emits light in a time of the order of about 10 raised to the power minus 8 seconds. So thus, if we have two independent sources of light, then the waves from the 2 points in the sources will have a definite phase relationship only for this much time, that is 10 raised to the power minus 8 seconds. And accordingly, the interference pattern formed by them will last on the screen only for this much time. The next burst of wave coming from the 2 points in the two sources may be having an altogether different phase relationship. So therefore, in that case, the positions of maximum and minimum of intensity of the light cannot remain fixed all along the screen. So students, do remember that by using identical independent sources of light, the condition 1 and condition 4 cannot be achieved, and accordingly, by using independent sources of light, sustained interference pattern can never be achieved. And as I mentioned, it can be achieved only and only by using coherent sources. That is, in order to obtain sustained interference pattern, the phase difference between the light waves arriving at a point on the screen from the two sources must remain constant with time. And this can be made only possible if the two sources are derived from a single source. And such sources which are derived from a single parent source are called coherent sources, right? In this case, a change in phase, if any, will affect the two sources equally. And moreover, the light waves from the two coherent sources will be of same wavelength, same frequency, same amplitude, isn't it? So it is only and only through coherent sources that sustained interference pattern can be achieved, right? Another point is, students, the two sources of light must lie very close to each other. The two sources of light must lie close to each other. It is because then the path difference between the light waves reaching a particular point will be very large if it is not so, right? And in such a case, the maxima and minima will lie very close to each other, and that might result in overlapping, right? This we will discuss mathematically as well. And students, one more point to be kept in mind is the two sources, light sources, should be very narrow. Actually, a broad source of light is equivalent to a large number of narrow sources lying together, right? So each set of two sources will therefore give its own interference pattern, and their overlapping will result in general illumination. So this is again the condition which is required. That is, the two light sources should be very narrow. The two light sources should be very narrow. So students, these are the conditions. Actually, the first four are the mandatory conditions for obtaining sustained interference pattern. And as I've told you, students, by using independent, perfectly identical sources of light, the first and the fourth condition cannot be satisfied. And therefore, sustained interference pattern can be obtained only when the two coherent sources of light are used. Students, if we make use of two coherent sources which are derived from a single source, then the first four conditions get automatically satisfied and hence sustained interference pattern is obtained, right? So students, in this particular lecture, we have discussed about Young's double slit experiment. Then we have studied about the superposition of the waves, the constructive interference, the destructive interference, the interference fringes, and then we have discussed sustained interference as well as coherent sources, right? So that's it for this particular session, students. Do revise the topic thoroughly, and in the next session, in the next lecture, we'll be discussing the conditions for obtaining constructive interference and destructive interference. We'll try to derive the conditions both in terms of phase difference as well as in terms of path difference, right? So that's it for this particular lecture, students. Till then, keep watching my videos and do join me in my next lecture then. Till then, goodbye and do take very good care of yourself. Thank you.